Okay, we're going to do another one. This is GES 2, which is March 2023, and I think this is one of the hardest papers of all time, which is why we're going to look at it. I'm going to run through it. I think there's some typos on here, and there's definitely some typos on the later questions, but some pretty wacky questions as well. Um, let's have a quick look. Section A looks alright, melting some ice. I don't think we've seen these ones exactly before, actually. So I think they're pretty new at the time, but we see them now a couple of times now, so quite familiar with it. Bohr's law, no problem. Usual stuff. Diesel engines, 8-cylinder, alright. A little bit tricky, but not too bad. Wacky units down here as well. What is that? That's just a bit crazy. But yeah, that was actually the first time we'd seen such things as well, so a bit tricky to do when we saw it first time. So have a look at that. It's not so bad these days because we've seen these things a few times now. Refrigerants and stuff, that's fine. Stoichiometric mass of air required and mass of carbon dioxide, not too bad. Yep. Weird, they gave us assume air is 23% oxygen, but they didn't give us the rest of the data, which is fine. It's alright. This is a killer question, and I'm going to try to go through it. I don't normally even bother doing it in class because it's so bad to go through. I'm going to take a long time to go through it, have to take a few takes at it because I'll probably make a mistake or five because it's so hard, but we'll try to get through it, we'll struggle through it. Two source electricity, that's nice and easy. Section B, of course. Hey, there's the same question we saw the other day on another paper. Maybe the numbers are a little bit different. Yeah, the voltages are different, but the same classic style setup. Yeah, definition question on primary, secondary cell. Lead acid battery, not too bad. Lenz's law and a conductor, usual stuff, that's nice and easy. Now this was a big problem. This caused a huge problem. This paper, there's a massive delay on the feedback actually to get your marks back. I don't know if it's I think it's because of this question, but it could have been because of internal discussions within the SQA. I hear things along the grapevine, and it seems like this is when the new guy came in, right? So the old guy quit. And if you look at I think he quit. From what I hear, if you look at the previous to this paper, so this is March 2023, and if you look at the December 2022, there's a lot of typos on that paper. And yeah, one of my guys recently, as we were reviewing it, it looks like the examiner was drunk when I was writing it or something like that. Like there's a lot of typos on there, and it's just bad English. It just doesn't even, the sentences don't even match up properly. But anyway, this is a new style of question. We haven't seen it before, and there's a typo on the question as well up here. I'm going to correct the typo and then solve the question. Because you can't solve it without this. So what happens usually when there's a big typo like this is they just remove the question from the paper and they mark it as if you're doing 11 questions instead of the full 12. So it's kind of a waste of time to attempt it. I'll do it just out of curiosity and we'll have a look through it. And it's not too bad once you fix the errors in it. So we'll talk about it as well. And then new kg after all the oil has been used. Again, this is a harder naval architecture question, finding the new kg is not too bad. We just build it into a table and solve it. Just ugly and tricky to have typos and new style of questions as usual. But like I said, we've seen these questions a few times now in the modern day papers. Okay, so we're going to start with number one, which is explain what is meant by entropy of fusion. Well, that's the amount of energy required to bring about a phase change between fusion is between a solid and a liquid, is fusing the molecules together, the atoms together to make a solid from a liquid. Okay, so that's not really that difficult for 2 marks. We can give the units as well. The units would be joules per kilogram, and it's actually given here entropy of fusion of water anyway, so for 2 marks they just want a sentence really, but I would always try to give the units and the formula as well. It's latent heat, but everything we just said is just fine. Alright, so let's do this 100 grams of ice. It's a classic question. We see this one in training just fine, not really a problem. So we've got 100 grams of ice at -5 degrees. So let's just be clear about what's going on. We're starting with ice, and this is at -5 degrees C. And then we're going to warm the ice up. We're going to heat the ice up until it gets to ice at 0 degrees C. And so it's going to heat up to 0 degrees C. Then it's going to melt into water. And that's still going to be at 0 degrees C. This is the phase change. This is the entropy of fusion part. This is the latent heat. And then it's going to heat up the water to get to the final temperature, and we don't know what this is going to be. I'll call it X degrees C. Okay, we're not actually looking at the states, we're looking at the parts in between. So this first bit here is going to be a Q mac T equation, Q is equal to MC delta T, and this is specific heat, which is heating up a solid, same way as we do with the quenching of metals and stuff like that, or a steel or whatever. It's just ice in this case, so it'll be a Q mac T. I'll call that part 1, or yeah, part 1. And then going from ice to water, this is latent heat. And that's where we're going to be using the enthalpy of fusion. This will just be a Q if is equal to M, well, technically it's L for latent, but I like to use C because it's the same as Q mac T, but without the delta T. You see there's no change of temperature there. And then we'll call that part 2. And then we're going to go from cold water to hot water, or warm water. We'll call that part 3, and this will be specific again. Specific. And this will be another Q is equal to MC delta T. Okay, great. So we're going to break it down into these 3 different sections, and we're just going to do part 1, and then part 2, and part 3. Okay, I just labeled them up so I can refer to them, but yeah, just underneath it, I could just write them down here. We're going to be doing a Q mac T for this first section, so Q MC delta T. Oh yeah, just to give you an overview of what's going on, is that we are going to be able to calculate the amount of energy required to do this. Like we know how much ice we've got, we know the quantity, the mass, and there'll be a certain amount of energy to heat the ice up to the melting point. There'll be a certain amount of energy to melt the ice, and then what we've got in the question is we've got 40 kilojoules, so whatever's left over in terms of energy will be then dedicated to heating the water up to its final temperature. Right, so we've got Q mac T for the first one, and we want to calculate how much energy is required. We actually know the mass of the water is 100 grams, so the mass won't change as we go through these different phases. It will stay the same. It's going to be 0.1 kilograms. The heat capacity of ice is given here as 2,110 joules per kilogram Kelvin. Let's write those down. And then the delta T, where we're going from -5 up to 0, so that will be a change of 5 degrees Kelvin, I suppose. We can plug all this in and calculate it, so we might as well. We're right here. So this will be 0.QMC delta T. I'll write that down here. Q is going to be 0.1 times by 2110 times by 5. Pop that into the calculator. So 0.1 times by 2110 times by 5, 1055 joules worth of energy. So this is equal to 1055 joules. We need 1055 joules in order to heat up the ice. Doesn't take very much apparently. Okay, the next part is going to be melting the ice, so we're going to use a different formula. We're going to use Q is equal to ML, or MC. I'm just going to use MC or ML. It should be ML, really. And we got the mass. The mass is not going to change. It's still going to be 0.1 kilograms of ice. The latent heat, well, this is this enthalpy of fusion of water, and it's 335,000 joules. It's incredibly large. It's absolutely massive. It's this many thousand joules per kilogram. So every kilogram that we have to heat to melt is going to take this much energy. Of course, the calculation, we're only using 0.1 kilograms, but the amount of energy will be 0.1 times by that big number. And I think that'll give me 33,500. So most of the energy is going to be used up here, just melting the ice. And this is why they say you shouldn't eat snow, because your body can't absorb solid water. It has to be liquid water. And just to turn it from solid to liquid takes so much energy. This is also the same principles behind air conditioning. We go from liquid to gas, gas to liquid, and it takes a lot of energy to change the state there, to change the actual shape of the molecules, click them over into a different formation. Okay, so we're using up this much energy. We've used up this much energy. We started the question with 40 kilojoules worth of energy, so it's 40,000. And for this next part, I want to know how much energy we have left over. So we started off with 40,000. It's like having a shopping list, and we've got this much to spend. We spend this much, and we spend this much, and how much do we have left? So we're going to minus off the 33,500. We're also going to minus off the 1,055. And we'll see how much we got left over in order to dedicate towards heating up that water. So 40,000 minus the 33,500 minus the 1055. We get 5,445. So we've got 5,445 joules left over in order to heat up that water. Now we're going to do a Q is equal to MC Q max T equation, and we actually have the energy this time, so that will be our Q. Q will be equal to the 5445. The mass is still the same at 0.1 kilograms. The capacity of water is given in the question. It's 4,180 joules. So it's 4,180 joules per kilogram Kelvin. And then delta T is what we're calculating. So we'll set that to be X. So here's my delta T, and this is equal to X. Now we just put it all together. So let's write Q is equal to MC delta T, just to be clear what's going on. This will be the 5,445 joules that we have to spend. We've got 0.1 kilograms, times this by the heat capacity, which is this much, and times by a delta T, which is X. Okay, you can see these guys, if I do it on a calculator, it will give me 418, but I'll just do it in my head. Kind of risky, shouldn't do that. And then we're going to divide this down to get the X by itself. So 5445 divided by 418 should just give me the X. So I've got that number in my calculator already. I will just divide it by 418. I get my answer as 13.0. So it'll be 13.0263 is equal to X, and we said that was equal to delta T, right? So we're going to have a 13-degree increase. And because we're starting at 0 degrees, because the water was at 0 degrees, that'll also be our final temperature. Usually you have to take initial temperature and add on the delta T, so 0 plus the 13 is just going to give us back the 13. No need to do it. So determine the final state and the temperature. So the final state will be liquid. I should actually say that. The final state is liquid. And it's going to be at final temperature will be 13.0263 degrees Celsius. We could do it in Kelvin if we want to be fancy, but I wouldn't suggest it, just in terms of typos. Pretty easy question. We've seen that question come up a few times on 2 papers actually. They changed the numbers a little bit, 2 or 3 papers, so quite a common question. It's nice and easy to get your head around as well because, you know, ice, water, nice and straightforward there. Okay, let's look at number 2. State Boyle's law, definition question, nice to have. Well, Boyle's law is like crushing an aerosol can, right? So a reduction in volume will lead to an increase in pressure of a gas. That's how I remember it. And we can embellish it a little bit. We can say that's for a perfect gas at a constant temperature. We're not forcing the temperature change at the same time. Okay, we're not also heating the gas, but really we're here for the calculations, so those are the difficult ones. So a perfect gas has initial pressure, temperature, and volume of this at 90 liters respectively, is cooled at a constant pressure until its temperature is 15. What's the initial gas mass of the gas? What's the final volume? Pretty straightforward, nice to have as well. Part A, because we got part 1, part I, we're going to use the perfect equation, PV is equal to MRT, and for part 2 we'll be using P1V1. T1 is equal to P2 V2 and T2. I'm just going to write down my P1 V1 T1 P2 V2 T2 straight away because they give it to me in the question up here. And as always, we're going to use all initial conditions for the perfect equation or all final conditions if it's more reliable, but I think it will be all initial conditions. Let me just pop those guys over there. We'll use them in a second. So I'm just going to write this down because I like to get the information out of the question. So P1 V1 T1 P2 V2 and T2, I am double checking that this is not like a 3-stage process, but I don't think it is. You can tell because it says in the wording like and then, but it's pretty sneaky, pretty subtle when they do it. So a perfect gas has a pressure of 2.75 bar. Let's convert this straight into pascals because that's how we're going to be using it. Not very difficult. We do it a lot throughout the course, so just fine. The volume is at 90 liters. Okay, let's get this into cubic meters. So that would be divide by 1,000, which we're quite used to doing with millimeters and all that. So I think it's 0.9 meters cubed. I can check it on a calculator, but I think we're all right. I will do it anyway, just to avoid silly errors on the exam. So 90 divided by 1,000 will get me 0.09 meters cubed. Great. And the temperature starts at 185 degrees Celsius, and we're going to turn this into Kelvin by adding 273 to it. So 185 plus 273 is 458. So this is 458 Kelvin. Okay, great. So that's all the initial conditions. I can use this for the Pervert equation to get the gas, but while we're here, we might as well get the rest of it. It's cooled at a constant pressure, so the pressure will be the same. I don't really need to write it down, but I will for the sake of completeness. And today's temperature is 15 degrees C. So let's convert this into Kelvin as well, because for gases we need everything in Kelvin all the time. 288, okay. So this will be 288 Kelvin, great. And of course they're asking for the final volume, so that'll be our X. This is a setup for part B actually, isn't it? So let's get part I, or I and II, not A and B, sorry. Let's get part I down here, because we're going to be using this Pervert equation for that. So we're just going to use all initial conditions. They've given us R here as 290 joules per kilogram Kelvin, so I can basically just plug the values into it. We're calculating the mass. I would always list these out and be like P, V, M, R, T, just out of habit. So the pressure was at 275,000 pascals. Check my units as well, just to make sure I haven't made any silly mistakes. We've got the meters cubed and the volume. Good. The mass is what we're calculating. The characteristic gas constant is given as 290 joules per kilogram Kelvin. And then the initial temperature is given as 458 Kelvin. Straightforward calculation. The PV is equal to MRT. The P is the 275. 0, 0, 0. The volume is 0.09. The mass is X. The R is the 290. And the temperature is 458. Nice and simple. We can multiply this together, and then divide down on the other side. So 275,000 times by 0.09. Real whole numbers. We can definitely write that down. And then the other side we can also multiply together. Might as well. So 290 times by 458, 1328. So it'll be X is equal times by X, and this will be 132820. And then these two are multiplied together, so we're going to divide it down. So we take this, divide them, we'll get this. Okay. So 24750 divided by 132820, and we get 1863, where this is the kilograms of the gas, isn't it? Well, that's quite confusing. I've got X up here, I'm solving for this mass down here. I shouldn't put them all together like that, but whatever. 0.18634, this is equal to X, and because I'm solving for this mass, it's definitely in kilograms. So this will be in kg, and this will be the final. This is the initial mass of the gas as well as the final mass of the gas. The mass of the gas doesn't change, so that word is a bit strange to have. It will just be the mass of the gas, or the final mass of the gas. It doesn't change in mass. There's conservation of mass, unless we're adding to it or subtracting it, which we're not. We're just keeping the same amount of gas. There's no changes. So this is the mass of the gas. I'd probably write initial, just because they say initial, but it's not necessary, is it? Because it doesn't change, right? That's part I, and then part II, which part 2 is what's the final volume. So using all this information, we're going to solve for the volume. So here's our P1, V1, T1 formula. Let's bring our data across, as well as the question, I suppose. So let's grab that as well. I'll just bring it all over here so we can see it all on the screen at once. Oh, let's make a bit of space. All right, scoot that across. Okay, so we're going to do the final volume of the gas, which is X. The pressure is kept the same because in the question it does say that it is cooled at a constant pressure. So the pressure can be removed from our calculation. There's no need to have it in there. The initial volume is, I've got all my units in the correct units, right? So the initial volume is V1. The T1 is going to be 458. And then V2 will be X. And then the final volume, final temperature, sorry, 288. Okay. So easy calculation, we just multiply the 288 to the other side. So I can just do that all on my calculator. 0.09 divided by 458, and then times that by 288, and we get a very small volume, but it is what I expect. Let's see. 0.05659. This will be, let's write down a couple of extra numbers. Let's keep it as a 4. This is equal to X, and X was the volume in meters cubed. So here it's 9 or 90 liters, here it's 56 liters, and that's because we went from a hot gas to a cool gas to a cold gas. So it's being cooled, so of course it's going to shrink. That's Charles's law in hot air balloons, right? So 0.056594 meters cubed is the final volume. Final volume, not so bad. Usually these papers these days hopefully are written quite nicely, as in they're quite all balanced, and there'll be these easy questions alongside the harder ones, and we can just do the easy ones. Okay, let's do number 3. See what it is. Whoop, let's make a bit more space for these guys. Okay. Number 3 is a diesel engine calculation to do with indicator power, brake power, and all that. These are quite chunky and clunky. They normally have quite a lot of parts to them, and they can be quite sneaky, and this one is a little bit sneaky. It's the first time we've seen such a thing go on down here. Look at all those, a mess of units. Kilonewtons over meters squared over millimeters squared over millimeters is a bit crazy. We're going to simplify that out as well. First of all, we're going to write down our units, our formulas. Sorry, let's write down all the formulas because we've got quite a lot of formulas. We're going to just try to do the first couple of formulas, the first 4. Technically, there's 8 formulas that go with this question, and that's a lot of formulas. So we've got the IMAP. This will be equal to the area of the ticket diagram multiplied by the spring constant divided by the length. Now we're going to talk about that a little bit because maybe we don't quite have that information, and they've given it to us in a slightly different way. Actually, they say mean effective height. If you read the question, it's an 8-cylinder 4-stroke diesel engine, has a cylinder bore of 350 mil with a stroke of 400 mil. Indicator cards were taken and each had a mean effective height of 22 millimeters. This is strange. They don't normally give it to us this way, and it's the first time we've seen a question written like this, so very difficult to deal with at the time. Mean effective height is actually what happens when you take the area and you divide it by the length. This is what's going on here, because usually you have a ticket. If you have the ticket, it looks a bit like this, a bit like a banana, as it goes through high pressure and low pressure. It has a little loop at the bottom. If I can draw that, I can't draw it. It has to go around, and I can't draw it. It looks like a banana, basically, and it might have a like very low pressure down here, and has high pressure up here. And what we do is we're going to find the average height of this, because up here is pressure. So we're going to find the average in pascals. This will be the average pressure if you turn it into a rectangle. And how you do that, how do you find the area of a rectangle, is you take, or the height of the rectangle, sorry, this is going to be the height of it, is you take the area and you divide it by the length. If you took the area, because the area of a rectangle is length times by height, and if you wanted to find the height, you can take the area divided by length will be equal to height. So this is actually what's going on with the calculation, and instead of plugging in the information like we'd normally get from these questions, we are given that straight away. They've like collected the information together and done the calculation, which is disorientating. So what I'm trying to say is area divided by length is effectively equal to the height, which is this 22 millimeters. This is equal to 22 millimeters. Okay, the next thing in the indicated mean effective pressure is that spring constant. And then we've got this really awkward 80 kilonewtons per meter squared per millimeter squared. It's not so bad. The spring constant is 80 kilonewtons, so that's 1,000 newtons. A newton meter is the same as a pascal. Newton meters is the same as a pascal, so this is pascals per millimeter. In terms of a spring constant, this means that for every millimeter that the spring is compressed, we have a pressure of 80,000 pascals. This is equivalent to 0.8 bar. Okay, so this is about right, because usually these questions are 1-to-1, like 1 bar for every 1 millimeter that the spring is compressed. Usually those the actual spring constant, you can almost ignore it, but in this case it's 0.8 instead of 1. So all of those things put together means that we can actually calculate the IMAP, which is equal to 22 millimeters of compression at the 0.8 bar. Well, and that will give us, I'm going to do it in bar because it's easier to see the numbers, and this will give us a pressure in the engine of 22 times by 0, on average pressure in the engine, 0.8, that's 17.6 bar. I'm working in bar just because it's easier to see. 17.6 bar. This will be the IMAP. Of course, this will be 1,760,000 pascals in terms of our calculation. I'm sorry I kind of jumped into that because this is the difficult part about this problem. The rest of the question is actually quite straightforward. That was the IMAP. And you see we don't actually need the IMAP directly, but we will be using it in indicated power. Let me get the rest of my formulas out as I usually would. After we've done the IMAP, we talk about the indicated power. So as IP is equal to X plan. That's just fine. Then we're going to have BP. This is equal to terminated 2 pi n. That's okay as well. Let's clean this up a little bit. Then we can have efficiency, which is the brake power over the indicated power. We'll times it by 100 to make it look good as well, but I'll just leave it like that. And then that's all we need for this one, I think. We don't have to go into the indicator specific fuel consumption or anything like that. So I'm not going to bother getting those formulas out. They're harder. We don't use them so much, so they're more difficult to remember. This is enough formulas to deal with, I think. So let's go for brake power, right? That will be our BP, I think. Yeah, we've got the information there. Again, there's always two ways to get into all these calculations. You can calculate the BP if you have this information, or you can calculate it from the efficiency if you have the rest of it. But it doesn't look like that's going to be the case. Okay, so let me grab the question and my formula, and we'll make some space for part A. Okay, there it is. So we're going to calculate the BP. The torque is given in the question as this much, right? It says it gives a steady state torque reading of 36,000 Newton meters. 2 pi is just 2 pi, and then n is the number of strokes per second. It doesn't matter if it's a 4-stroke or a 2-stroke, it's just number of strokes per second. So we're going to start out for the BP one. So we're going to start off with 800 revolutions per minute, revolutions in a minute, and we'll divide it by 60 to get it into revolutions per second. So let me do it on a calculator. I'll get my 800, we'll divide by 60, and we get that out as 13.3. So this is equal to 13.333, and this will be revolutions every second. Now it's just a case of putting it all together and multiplying it. So the BP will be equal to 36,000 times by 2 pi times by the 13.33333. All right. So I've got that 13.333 still in my calculator. I'll times it by 2 pi, and then we can also times it by 36,000. While we're here, big numbers, big engine. Let's see. I get that as 30, 15, 92, 8.9. That is, that's 3 million. So this many watts. So it's a 3 megawatt engine. All right, that's a big one. It's running at a very high pressure, as we just saw. So I suppose that's why it's such. It's an 8-cylinder. So yeah, fair enough. All right, so that's part A. Indicated power is part B. So we're going to use IP is equal to X plan for that one. Okay, probably, or maybe the efficiency calculation. But of course, you can see we've got the efficiency down here for part C. So we're not going to do that. Let's list out the ingredients. We've got X, this is the number of cylinders, where it's an 8-cylinder. P is the indicated pressure. This is what we calculated at the very beginning. And it was the sticking point. It's the two difficult parts of it. First of all, the confusion over how to put this IMAP together. Like I said, we'd never seen that before in this paper when it came up. So now we have, but still these are difficult problems to attack, right? So I got that as the IMAP came out to be 1.7 megapascals. So that's my pressure. I did calculate that earlier. And then L is the effective length of the stroke, which is 400 mil, so that's 0.4 meters. A is the area, so we've got the bore as 350. So I'll do my little quick calculation of 350 divided by 2000, square that and times it by pi. We're taking the diameter in millimeters, dividing by 2 to turn it into a radius, and then dividing by 1,000 to get into meters, and then doing pi pi r squared on it. And it's just to save me doing a side calculation. You can do it any way you like. You can do the side calculation if you want to. It's just fine. Now n is the number of effective strokes per second. And we already did a bit of calculation on this. We took it from 800 revolutions per minute. We got it down to 13.333 revolutions per second, but we got to take it a little bit further because it's a 4-stroke engine. If it was a 2-stroke, we can just leave it as it is, but not every stroke is a power stroke on a 4-stroke engine. So we're going to take the 13.33333 and divide it by 2 to get the number of effective strokes per second. This is going to be 6.66666 effective strokes. So let's write it down per second. Okay, now I'm going to calculate my area as a separate calculation, and then we just multiply everything together. So I'm going to do the 350 divided by 2000 equals square it equals times it by pi equals. This is the cross-sectional area of the piston, okay, in meters. So it's 0.09621127 meters squared. Doesn't seem very big. 350, just double check that. I mean, it is 35 centimeters across, so it's pretty chunky. 350 divided by 2000, so you kind of expect it to be a little bit bigger. Square it, times it by pi. Nope, it's definitely that. Alright, so now we've got all our bits of information. We're going to multiply them all together. IP, therefore, would be the 8 cylinders times by the very high pressure. The reason why I say such a high pressure is because we haven't seen this pressure on these types of questions before. We normally have, like, the lowest type of pressure will be about 5.5 bar. And this is 17 bar, right? So it's much higher than usual. It is, at the time we did the question, it was the highest pressure we've ever seen in the last 5 years worth of papers, basically. So let's plug our values in for the length. Then we've got the cross-sectional area, as usual. Lots of data to multiply together. And then for just 2, this is the usual style. And then the number of effective strokes per second. So all those numbers to multiply together. And the good thing is we can check it against our BP because the BP was an independent calculation. And this is 3 million. I do expect my IP to be a little bit higher, right? IP is the theoretical power of the engine. And of course, the comparison with this will be our efficiency, the mechanical efficiency. So I've got this number in my calculator already. We'll times it by 6.666, times it by the 0.4, times it by the 1760,000, and times it by 8. Yep, so it looks good because it's very similar. It's just a little bit higher than the BP. So I got my IP to be 3,612,412.3 watts. So this is the indicated power of 3 million, 3.6 million. The BP was 3 million. So this is the actual power, and this is what it could be producing. And a comparison between those, of course, will be the mechanical efficiency. So let's do the efficiency down here. The efficiency will be equal to the BP over the IP and times by 100. So we're just going to pick up our numbers from the last part of the question. Once we get to this stage, it's nice and easy. But the problem is we have a hard time getting to the IP because of that, because of this calculation to do with all the IMAP. You just get stuck at it. You can normally do the brake power, no problem, but getting into this, understanding all those awkward units is just so difficult to do unless you've seen it before. And like I said, the first time we did this in the paper, we had never seen stuff like that before, so difficult to deal with. Alright, that's why I'm going through these videos. Okay, we'll times it by 100. So it looks like it's going to be a high efficiency. It's usually around like 88% or something like that. I got this number in my calculator already. We can do 30, 15, 928.9 divided by the answer, times it by 100, 83%, that's just fine. Okay, so the efficiency is 83.4879%. Efficiency, that's the mechanical efficiency. Great. We don't have to do any of the indicated specific fuel consumption, so that's nice, but those units are screwy. Okay, let's look at the next one. Number 4. Number 4 is a definition question. State 2 desirable properties of refrigerants, no problem. All the rest of the usual stuff, just standard definition questions for the refrigeration plant. Number 5 is a combustion question, so these are a little bit tough, a little bit long, but this is pretty standard, so let's go through it. 1.5 kilograms, they give us the amount of fuel, that's good, of C3H7 is completely burned in air. Determine each of the following: stoichiometric mass of air required and the mass of carbon dioxide in the exhaust gases. So this is our standard approach anyway, it's not going to be too difficult. We're going to start with hydrogen is equal to 1, carbon is equal to 12, oxygen is 16, and air is 23% oxygen, which they give us that one piece of information, but nothing else. Is strange. 23% oxygen by mass. Okay, and we are going to have a look at the carbon. We've got to see how much carbon do we actually have in C3H7 and 1.5. So we've got carbon over here, and we've got hydrogen, and then we have a total. Okay, so the carbon is, we've got 3 of them, so that would be 3 times by 12, which is equal to 36. The hydrogen, which is 7 of them, so 7 times by 1 is equal to 7. The combination of this will be the total, so 36 plus the 7, that will be what, 43, I think, but I don't want a calculator because I don't want to mess it up. 43, okay, total of 43. That allows us to calculate the percentages or the parts by weight. So 36 out of 43 parts will be carbon. We've got 1.5 kilograms in this case. So we're going to calculate that to give us how many kilograms of carbon there are in 1.5 kilograms of the fuel. We'll do the 7 out of the 43 times by the 1.5 to get the kilograms of hydrogen per 1.5 kilograms of fuel. And they should add up to be the total amount of the 1.5 kilograms as well, so I can double check it that way. So 36 divided by 43 times by 1.5. This gives me 1.2558. Slightly awkward numbers. 1.2558 kilograms of pure carbon to burn. Alright, and then the same thing on the other side. We're going to do 7 divided by 43 times by 1.5 to get 0.244 kilograms of pure hydrogen, 0.244186 kilograms of pure hydrogen. These two numbers should add up to be the total of the 1.5 kilograms of fuel. I do check this. I do use this to check my students' work because it's just a nice little checkpoint, you see. We got 1.5 kilograms of fuel. Great. Now we're going to burn the carbon and we're going to burn the hydrogen. So let's burn the carbon. We're also going to burn the hydrogen. So these are our formulas, and they're always the same. We're going to take carbon, add in oxygen, and we're going to make CO2. So we better balance this out with a little 2. So C plus O2 is equal to CO2. That's because it is completely burnt, not partially burnt. So it's a technical term. And the same thing with the hydrogen is hydrogen plus oxygen is going to be H2O. So this is going to be a 2. Okay, right, looks good. And we're going to use that little formula of the number of moles, because we're saying 1 mole of this and 1 mole of that should make 1 mole of this. It's like you could think of it in 1 portion of this, 1 portion of those would make 1 portion of that. And this is why this is a lot easier than the usual way. So the number of moles is going to be the mass of the carbon divided by its relative atomic mass. And these are going to be equal, 1-to-1 relationship. We're going to use that on both sides, so I'll pop it over there. How much carbon do we have? Well, we got 1.2558 kilograms of carbon. We'll divide that by 12, and this will be equal to the amount of oxygen divided by, it's 2 oxygens, so it's 16 plus 16, so the whole thing weighs 32. And we're going to solve the little equation to work out how much oxygen we require. Okay, same thing on the other side. We're going to take the amount of hydrogen, which is this number here, the 0.244186, divide that by 2, and this will equal to the amount of oxygen that we need, and it's only a single oxygen this time, so it's just going to be a 16, and we're going to solve this equation. Right, so let's solve these. We just multiply the 32 to the other side for that first one, so it's going to be 1.2558 divided by 12. We'll times that by 32, and it gets us 3.34. So this is going to be 3.3488 is equal to X, and this is kilograms, right? So I'll just put it straight into kilograms, and so of oxygen, so we need, let's just keep it like that, of this many kilograms of oxygen is required to burn the carbon. Okay, so we need 3.38. This is a stoichiometric amount of oxygen to burn that carbon, the minimum amount of oxygen. We're going to do the same thing over here. We're going to take the 0.244186 divided by 2 and then multiply the 16 up to the other side. So let's do that. 0.244186 divided by 2 and then times it by 16 and we get 1.95. So this should be 1.9534 kilograms of oxygen is required to burn the hydrogen. Alright, that looks good. Okay, let's see what the question asks for, because that's really our halfway point. They want the stoichiometric mass of air required. So let's bring the question down so we can see it, work with it. Minimum amount of air required. So we can add these together to get the stoichiometric amount of oxygen, and then we can work that into stoichiometric amount of air. And that is a little step in. There's only 2 stages of working. So let's do those 2 stages. So first of all, we're going to say stoic ox, and that should be equal to the amount of oxygen here for the carbon. Stoichiometric means for the total amount of fuel, right? It's not the same as per kilogram, which will be specific. Okay. But it's just for everything. So that's why we've got to use the 1.5 kilograms. We're going to add these 2 together, and that should give us the stoichiometric amount of oxygen. I've got that number already in my calculator. Let's add on the 3.3488. Give me 5.3. All right, so this will be 5.30288 kilograms of oxygen. This is stoichiometric amount of oxygen. And now we can work this into stoic air. The stoichiometric air, and this is at 23%. So some amount of air times by 0.23 has to give me 5.3 kilograms worth of oxygen. So how much air do we have to bring in order to get that oxygen out of it? So we're going to do a reverse percentage calculation. We take this number and we divide by 0.23. That should bump it up and make it bigger. So here it is. That number's still in my calculator, just keep processing it. And now we get 23. That's suspicious, isn't it? Very suspicious. That's what I don't like about these numbers that the guy uses, is that they make you second guess yourself. Okay, so we need 23 kilograms. So we need 23.0534 kilograms of air. This is the stoichiometric amount of air required for part A, and that's how much the minimum amount of air we need to bring into the engine in order to completely burn that fuel. Realistically, we're going to add in a bit of extra. Usually, not in this one. Normally there'll be excess air, and there's no excess air in this one. We're just going straight from mass of carbon dioxide. So it's completely burnt just at the stoichiometric ratio, which is, yeah, that wouldn't happen inside of an engine, I don't think. It would happen inside the lab though, so this is obviously a laboratory calculation, which is a bit strange, right? Normally there'd be excess air, so not this time. Mass of CO2 in the exhaust gases. Okay, so the only place CO2 comes from is right here, because there's no CO2 in the atmosphere as far as we're concerned. So in order to get the mass of CO2 in the exhaust gases, we just take the mass of the oxygen required to burn that carbon as well as the mass of the carbon, and we add the 2 things together. Let me write that down. So for part B, the mass of CO2 will be equal to the mass of carbon plus the mass of the oxygen required to burn that carbon. So what's the mass of the carbon that we're burning? We're burning 1.2588 kilograms of carbon. What's the mass of the oxygen to burn that carbon? It's 3.3. Okay. So if we add these 2 together, we should get the mass of CO2 produced. So that's 1.2558 plus 3.3488. Gives me 4.6. So we get 4.6046 kilograms of CO2 being produced for every 1.5 kilograms of fuel being burnt. And that should be it. Okay. Now we're going to try number 6. And number 6 is the one I've been dreading, is the hard question. The very hard question. I would not recommend you do this one in the test because it's diabolic. It's one of the hardest questions I think that exists on these papers. The reason why it's so difficult is because it's vertically stacked. So you have to calculate part A to get to part B, and then part B to get to part C effectively. Maybe not quite. Maybe you can get part C from part A. But if you make a mistake along the way, everything's going to be wrong. And that used to be a problem on the earlier papers. I think these days they give you method marks. They've just changed it. In 2025, 2020, end of 2024, they just changed. Can't be sure because the whole process is a black box. But we're going to have a look at this problem anyway. It's an interesting one, but it's a really hard one to do. So at point 1 of a cyclic process, 0.2 meters cubed of air at this pressure and this temperature occupies a cylinder at bottom dead center. Assume losses are ignorable, negligible. Can't say negligible, so I'll say ignorable. At top dead center at point 2, the gas is being compressed to 1/10 of its original volume. Determine the pressure assuming no temperature rise. So that should be fine. We can probably do that part of the process. Then we're going to do some more afterwards, and at top dead center there's a heat addition of this much, which causes pressure to rise. This is done in kilojoules, and then we're given a CV, which I'm going to have to use a Q-Mac-T equation to solve, which is just fine to do. But we don't normally use Q-Mac-T for gases. We normally use it for solids and liquids, but we can use it for gases as well. Okay, so we're going to give that a go. CV. Why is it called CV? That's interesting. Okay, let's give this a go for part A then. So part A, at top dead center is being compressed to the original volume. So we've got point 1, point 2. So I guess we can call that P1, V1, T1. And then P2, V2, T2. Let's have a quick look just to see if there's another gas equation on this paper so far. Because it'd be strange to have them. Yeah, we've already done a gas equation. So why are we doing another one? Sometimes they do that, right? And we already did a Q-Mac-T already as well. So why do we have a Q-Mac-T and another gas equation here? I don't know. It's just because it's a very difficult problem. And this was the new examiner's first paper, so I guess he wanted to make a splash. So at point 1, there's a cyclic process. We've got 0.2 meters cubed of air, and it's at 1.1325 bar. I should convert this straight into pascals. I could have done that straight away, right? Would have saved me the space on my page. Let's write them in. This is equal to 101,325 pascals. Okay, and at 20 degrees C, let's convert that straight into Kelvin. So this is 20 plus 273, which is 293. So 293 Kelvin. Okay, and it occupies, yes, okay. That's just fine. At top dead center, the gas is being compressed to 1/10 of its original volume. So the volume is now going to be 0.02, and the temperature is going to be kept the same at 293 Kelvin. All right, well, if the volume is reduced, then the pressure will be increased, and it will be by a factor of 10, so this will be 10 bar. But let's do the calculation. Determine the pressure assuming no temperature rise. That part is okay for 2 marks, 2 little marks. So we're going to do P1, V1. So we're going to do P1, V1, T1 is equal to P2, V2, T2, but we're going to keep a few of these the same, right? We're going to keep the T1s the same like that. So we're just going to plug the values in. Even though we already know what's going to happen, I wouldn't rely on like gut instinct or whatever. I would do the calculations. They're not very difficult to do, and they're much more reliable. It just saves us making silly mistakes. When you're under pressure in the exam, you know, we want to back this stuff up with calculations. You should also show you're working as well. So this is fair enough. All right, so Let's type this in, 101,325 times by 0.2, and then divide that by 0.02. And that number is the same, but with an extra 0 on the end. Not very clear to see. So the final pressure, or the pressure at this point, will be 10,13,250. Let's add some commas in. Yep, it's now 1,000,000 pascals instead of 100,000 pascals. So it has increased by a factor of 10. That will be the pressure right here. We can write that in as 10,13,250 pascals right there. Okay, that is at top dead center. At point 2, the gas has been compressed to 1/10 of its original volume. Determine the pressure assuming no temperature rise. That is part A. This will be the pressure right here, assuming no temperature rise. All right, nice. That's fine so far. Now we're going to do part B, which is at top dead center, there's an addition of 60 kilojoules, which causes the pressure to rise at a constant volume at 2.3. Okay, so the piston's not really moving, but there's an addition of heat energy into it, right? So obviously this is injection and ignition of the fuel. Let's bring all this across. Keep that where it is, and we'll bring a copy across. Okay, so we're going to have to do a Q Mach T equation on this. You can see we've got a R and we got C. So I want to do a Q is equal to mc delta T equation on this. And in order to do this, I need the mass. And I was just thinking about why am I going to use this this R? And of course, I'm going to use the Pervert equation, the PV is equal to mRT, in order to calculate the mass of the gas as well, I suppose. Let's see if we can do that, right? Because at top dead center, we have a heat addition. So this is 60,000, so Q is equal to 60,000 joules being added in. I don't think I know the mass of the gas. There must be something I'm missing from this. I'm not quite sure. Let's just see what happens, right, when I plug stuff into it. The mass we don't know, so we do need that in order to do the calculation, right? We've got 0.2 meters cubed of air at this pressure. So I could probably calculate it from all this. That's probably what I'm going to do. Let's get everything else. The capacity is going to be 718 joules per kilogram Kelvin. That seems okay. And then we got the delta T, which is the change in temperature. Okay, and it says no temperature rise. So no change in temperature. So what? Delta T is equal to 0. If delta T is equal to 0, this Q Mach T doesn't work. So that's interesting, isn't it? How are we going to do that? Don't know. I obviously need a modified formula, so I'm going to go look that up. Let's see if we can do the other side. We've got the P, the V, the M, the R, and the T. It does say per kilogram Kelvin, but then there's no temperature rise. So there's no Kelvin, no delta T. That's interesting. So PV let's see, we got the pressure. So it's compressed, yeah, at top dead center, it causes pressure to rise at a constant volume to 0.3. Determine the pressure as a result of this process. Oh, maybe I don't even need any of this. Causes the pressure to rise at a constant volume. So this will cause a change of temperature, right? If you're in this change of, let's see, we got the pressure, which is, it's being compressed to 1/10 of its original pressure. Like I said, I told this was a hard problem. So this is a tenth. This is the 10th of the original volume as well. So I'm using P2 and V2 at this point because we're at the compression stage, right? So we have to use this new pressure, which is P2, and then I'm also going to use T2 as well. Okay, right? So I'm going to see what I can do with it. The volume is also now going to be 0.02 because that's the new volume after we compressed it, right, to 1/10 of its original volume. So this is going to be the volume of the gas. We've got the R value there as being 287 because it's kilojoules, so we times it by 1,000. So this is going to be joules per kilogram Kelvin, joules per kilogram Kelvin. Okay, and I don't know the mass of the gas, but it'll be the same mass as this one over here, but we can calculate the temperature if we knew the mass of the gas. I suppose I could calculate the mass of the gas from the starting condition. So I don't know its temperature here, and the temperature is going to increase. So that's what I want to know. What will be the new temperature? That will give me the temperature change. Oh yeah, that will give me the temperature change for this bit. So I'm going to have to use the pervert equation on the initial conditions to get the mass, and then I can plug it into this one. Maybe I could have done that a little bit better, and I probably could have done it a little bit better. So now we're going to use the PV is equal to MRT using initial conditions. So this will be P1 V1. The mass of the gas is going to be constant throughout, right? So I want to work out the mass of the gas. I don't know how much 0.2 cubic meters of air weighs. So that's where I should have started on the actual question. All right. So we've got P1. These are very, very difficult numbers to work with because they look very similar. It's 101,000. This is a million. 325 pascals. That's fine. The volume, original volume was 0.2 meters squared cubed. That should be a cube, shouldn't it? Yeah. Okay, and then the mass of the gas is what we're trying to calculate. We got the gas constant here as being 287 given in the question, joules per kilogram Kelvin, joules per kilogram Kelvin. And then we got the temperature 1, which was the initial temperature of 20 degrees, which we've already written down here as being 293. Yeah, finally, we get a way into this question. There's some of the harder questions are like this, where you have to basically search around in order to do them. I mean, obviously, if you practice this question, this exact question before, then we can do it, right? And you know, you've already got it memorized. I don't usually say we should do this one in class or even in the exam or even in class because it's so long and confusing. I think we should learn the basic stuff first, the easy stuff, the medium stuff, and then if you've got the time, you can have a look at these. I really just think they're included occasionally. Nobody's really realistically going to do this in the actual exam because it's so complicated. Maybe if I approached it the correct way around to start with, it would have been a little bit easier. Okay, so now we've got this red part and we're going to calculate the mass of the gas. We're basically just going to plug the values into it to solve it. So let's do that. Where can I put this so I've got space to do it? I think I'll be fine. So the mass of the gas will be, so this is finding mass of the gas. It will be constant throughout. Except from when you inject heat energy into it, how is that heat energy injected into it? It wouldn't be through injecting fuel into it, and we don't know the quantity of fuel being added into the mix. So that's a bit strange, isn't it? That's really strange because we're doing it at top dead center. We're just injecting heat energy, but no extra pressure, no extra mass. So what are we doing? Just heating up gas, just heating up the air. We're just burning air by itself. We're just heating up the air. That's strange, isn't it? I suppose if the fuel was already part of that air, that would be all right. So it's already part of the air, and then it comes up and it ignites. That would be okay. And then that will give you this addition of heat energy without changing the mass if the fuel is already mixed in here. All right. Just trying to get it straight. Okay, so mass of the gas plus fuel, right? So actually, yeah, that is possible. All right. We're going to plug these in. We got the PV, so that's the 101,325 times by the volume, which is 0.2. The mass is what we're calculating, and the 287 and the 293 is going to be the rest of the numbers. We're going to multiply all this together, divide it down, we'll get the mass of that gas. Let's do that. Careful on the numbers because they're all very similar. 325 times by 0.2. That's nice, a whole number to work with. So 2265 is equal to, and we can multiply together the other two over here, the 287 times by the 293 to get 84. So this is 84091x. Okay, divide the x, or divide these numbers down to get the mass of the gas. Let's see how much 0.2 cubic meters. 0.2 cubic meters is 200 liters. That's quite big, isn't it? 200 liters. I guess it's quite a big engine. So. Huge pistons. All right, so we're going to take the 2265 divided by 84091. Let's do that. We'll get this in cubic meters. No, kilograms. My bad. So this is going to be equal to 0.2409889 kilograms of material, of air mixed with fuel, I reckon, right? This is how much it weighs. Now I can use that to plug it in here to find the temperature of the gas after these changes have happened. Then I can use that to work out, or I can use the, why can't I just calculate it from this? What do we need to calculate? Determine the pressure as a result of this process. Oh, I'm calculating P3. This is P3. Pressure rise at constant volume. At top dead center, there's an addition which causes the pressure to rise at a constant volume to 0.3. Yeah, I'm calculating P3. And what I'd like to know, no temperature rise. This should give me the same temperature. Oh, it will give me the same temperature. Because what's happened is for part 2, that's what I'm saying, it's so confusing. I could make this a little bit clearer. I shouldn't have done it live like this. I should have done it carefully thought out. So the temperature will be the same because the volume has decreased and the pressure has increased, and they cancel each other out, and you'll get exactly the same numbers on this P on this perfect equation for part 2 for part 2. I'm just thinking if I could have done it another way. I could have done this exact same process on P2 and it would give me the same answer actually. I do need the mass of the gas though. So I was searching around for it and I could have actually done it from here. I don't know why I didn't. I didn't know the temperature, but I did because it says same temperature. So I added an extra step for no reason. But this is the mass of the gas. I can confirm that. Let's just confirm that, right? So if we actually know the temperature at part 2, no temperature rise, yeah? So that will also be 293, and I'm just going to get the same equation. I'm going to get a slightly different numbers, just really careful on these numbers. This is the PV, and that's now 1,000,000, and here it was 101,000, right? And here the volume is 0.02, and here it was 0.2. That's 10 times smaller, that's 10 times bigger, and this is 10 times bigger, that's 10 times smaller. So they cancel each other out. And we're going to get exactly the same calculation. So that would be, let's just do it, MRT. And the mass is what we're looking for. So we should get the same mass. I'm going to get the same calculation. I'm going to get 0.24 on this as well, right? The gas is still 287, and the temperature is still 293. Yeah, you see this side is exactly the same, 287, 293. And we're going to get the same mass of the gas. So we're going to multiply the left-hand side together. So it'll be 10,13250, hopefully, times by 0.02 equals, and divide that by 287 times by 293. All right, and we get the same mass of the gas, right? We got 0.24. So I could have saved myself the stage. I didn't have to go through the stage. I just went back to initial conditions because I forgot that I didn't see this. That is constant temperature. So it is constant temperature. So the mass is confirmed basically as being 0.240988. Okay, so now we've got the mass of the gas. We can plug it into here. So this is going to be 0.240988 kilograms. You know what it was? Is I was confused between this blue section is stage 2, and then we are calculating the temperature at stage 3 here in black. That's what it was. Top dead center is additional. This causes determine the pressure. So there's a temperature rise. So let's calculate the temperature rise. And it does say that, doesn't it? There's an addition of heat, right? So addition of heat energy will cause the temperature rise, and that will cause the pressure to rise. Yeah, that's Charles's law. No, Bohr's law. No, it's neither of them. It's neither of them. It's just heating a gas will cause the pressure to increase. Okay? All right. Yeah, okay, so let's get out the temperature change from this thing. So this is going to be a Qmac T, and I'm going to plug the values into it. Let's bring all this down to a place where you can work on it. Okay, so let's calculate the temperature change here. So this is going to be 60,000 joules of energy injected into the system, and that will be the mass of 0.240988. The C is the 718, and then the temperature change is X. That's what we're calculating. It's called X. Okay, multiply these together and divide it down. Not too bad. Let's take this, times it by 718 equals, so that's the right hand side done, and then we take the 60,000 and we divide it by this. We get 346. So 346.76 is equal to the temperature rise. So that's what it's going to cause the gas to get hotter. As the gas gets hotter, we're going to increase the pressure. So now we're going to do a P1 V1 T1 on this, I suppose. Yeah, we have to, right? P1 V1 T1. Temperature, change in temperature. So we got to accommodate that because we need the original temperature, don't we? So the temperature was at 293 Kelvin or 20 degrees C, and now it's going to be a lot hotter. All right, okay, so now we're going to look at, what's the question asked for? Pressure? Okay, so we're looking at P2, P2, V2, T2. Man, this is so hard. P3, V3, T3. Okay, so P2, V2, T2, and then P3, V3, T3. Like I said, I could have laid it out a little bit clearer. But it's such a chunky question. What are you going to do? Like, get organized on it? What I didn't want to do is get everything like really well prepared and then show you how I got it really well prepared, because it makes it look easier than it really is. It's a really nasty question. That's why I wouldn't recommend doing it. It's better I do it on the fly so you can see the struggle. It's quite embarrassing and annoying to flounder like this, but it's true, and this is what I want you to avoid in the actual test, right? I don't want you to do this because it's so nasty. So let's get the data from the question up here. We got P2, haven't we? We got all this bits of information. We know we're at this many pascals. Yeah, we got all these bits of information. This is all for P2. I can just bring all this down here. All of this is for part 2. Part 3, let's see. Do we have the information of part 3? Well, there's a temperature rise. We just calculated this. The temperature rise is the 346 increase. So I suppose I'm going to take my 346, add that onto the 293, and we'll get the temperature is now at 639.76 Kelvin. Let's keep all this P stuff for P2. Let's keep it in blue. Let's get this in black. This is in Kelvin, right? I think it says in the question that we remain at a constant volume, yeah? It says constant volume. So we're going to keep the volume the same, which means I don't really need to include it in my calculations. And the question is, what's the new pressure, yeah? Determine the pressure for 6 marks. So nasty. X. Alright, so we get our P1, V1, T1. And we do not need the volumes. And now we can plug in everything else. That's the pressure. That's the temperature. We are calculating new pressure, and the new temperature after that heat addition is this guy. Fingers crossed this is going to work. Let's see what we get. Increase in temperature will be increase in pressure, probably, right? So we're going to multiply this 639 to the other side. So basically we're multiplying this by 10,13250 divided by 293. Fingers crossed. High pressure, which is kind of what we expect, right? I don't know what to expect anymore after this question. 345 is equal to X. So let's get that into some numbers. 2 million, so 22 bar, which seems okay. That seems all right for an engine, right? 22 bar at the point of ignition. And this will be in pascals. Is that what they wanted? It probably was. By this point, I've completely blown up my exam. If I was doing this live in the exam, because it's taken me about half an hour just to get through this question. I don't know how long it's taken, but it feels like forever. Okay, determine the pressure as a result of this process. That's probably it. The cycle continues with an expansion from this point back down to point 4, which is bottom dead center. Determine the final pressure at point 4 if the temperature remains a constant in this process. When we're at point 4, we're at bottom dead center. Didn't we start at top dead? We start at bottom dead center. So wouldn't the volume be the same? Right? As we go through the process, we go up and then back down again. Surely the volume will be the same. What do they want to know? The final pressure at this point if the temperature remains constant. This is what I'm saying about this question, is that you have to make assumptions, or you got to jump back to the first part in order to get the last part. Because we're now at point 4 at bottom dead center, I think that the volume will be the same. Let's see if we can let's see if we actually have to use that. So we're going from P3 to P4, so it's a 4-stage process. So let's just get P1 V3 T3 is equal to P4 V4 T4, and then we'll see if we can list out the ingredients of P3 V3 T3 and then P4 V4 T4, and see if we can avoid that assumption or if you actually have to make it. Okay, so what do we have now? Right, the cycle continues with expansion. So the volume is going to go back up to, hopefully, well, I think it's going to go up to 0.2. Careful on the numbers. If the temperature remains a constant in this process, the temperature, yeah, that's interesting because we had to calculate the temperature. So we've got to rely on all our calculations. So the temperature was this. Oh, I've actually got all the information, haven't we now? For P3. These are the values. That's there we go. And then the P3 we just calculated at the end. That was this 22 bar, or 22 million pascals. All right. So it's messy, but I don't want to spend the rest of my life doing this question. Okay. So then P4 is if the temperature remains constant. So we've got these hot gases, and they stay hot. Okay. Then what else changes? Well, like I said, we're going to have to make an assumption. In order to calculate the final pressure of the engine, of the cylinder, well, we have to assume that the volume is now at 0.2 meters cubed. And the only place I can get that is from the very beginning, because they say we're back to point 4, which is the same as point 1. Because we're at bottom dead center, and here we're at bottom dead center. So logically, the volume should be the same. All right, and we're going to calculate this guy. Everything else is going to change. Nothing else is going to be kept the same. So we've got to plug them all into the equation, and hopefully we get through this question. I should have practiced this one time before the question, before I did it live, but whatever. It's nasty. Even if you practice it, I wouldn't bother. It never comes up. It's like a very rare question. If it does come up, you will know everything else on the paper. You'll be able to approach everything else on the paper, and you don't have to engage in this problem. It's basically, oh, the temperature's kept the same. Oh, nice. Oh, it's basically like a honey trap. It's designed to suck you in, and you start puzzling over it. And like I said, I actually don't think we've seen this question before either. On a previous paper, I think it was a new one. I can't remember. It's a couple of years ago now that this question came up. Anyway, this is 2023, right? It's 2025 now. So a couple of years ago, this was probably the first time we'd seen it, or the first time in a very long time. If I look through the question bank, I'll see it. Right. Okay. So final thing. Well, you can see what's going to happen is if the volume is going up by a factor of 10, then the pressure will go down by a factor of 10. Right? So I can already tell that's going to happen. We'll times this by 0.02, that's the left-hand side. We'll divide it by 0.2, and we get similar numbers, which is very confusing. You've got to not make any typos on that when you copy them out. And knowing that things change by a factor of 10 is helping me out a little bit. So 221241.43 pascals. So now it's at 2.2 bar. And this is the final pressure, probably. Calculate the final, determine the final pressure. Yeah, that's probably right. For 2 marks, the whole question's just not worth it. It's so gnarly. I mean, I know I made a mistake over here. I didn't really have to do that part of it. I could have got it better organized. But the reason why I don't do it in class is because just to that one question, to get it organized, to practice it, it's an incredibly difficult question, mixing together, you know, multiple disciplines. We're using the pervert equation and the QMAC-T, which we never do anywhere else. We could spend an hour or two practicing that in class, and it ends up not being worth it. I mean, what's the point? Really, what is the point? You're not going to do it in the exam. It takes too long to calculate it. Even if you had it down like to a T and you could do it very quickly, it's very risky as well as a question because it's vertically stacked. You've got to make some assumptions. You've got to make some calculations on there. These are just generally throughout the papers. There's some vertically stacked questions where you have to calculate part A to get part B to get part C, and I would suggest that we don't do those questions because if you make a mistake, the whole thing's wrong. But that's probably right. Did it. Next one. Okay, so on to the next one. Number 7. So you can find it. Okay. Number 7, just a definition question, nice and easy. State 2 sources of electricity. Well, yes, okay. These will be pretty easy to do. We don't need to go through them. Describe the characteristics of a conductor, good insulator, all that stuff. Okay, so we're back onto the electronics section, and this is like the classic setup. We've seen this question come up quite a few times, slightly different numbers. We just got to check the diagrams, make sure there's no typos on there. Alright, let's make a bit of space for this one, because it's going to be a bit of a long one, to break all this down, to follow it through. Battery terminal supply voltage, and then the current at these points. And we've got a usual approach. We're going to draw out the circuit diagram. Again, I'm going to sacrifice speed for clarity. So I'm going to take my time over it and do it nice and slowly and clearly, and we should be fine going through this. Okay, let's draw out the circuit. We've got these components. Just make sure you got all on there. And this will be our 40 ohm, 80 ohm, 100 ohm. The 3 ohm internal resistor, and this is 120 ohm. And I should hook these things up to each other, shouldn't I? Let's see if we can get it on there. Oh, come on. Let's hook it up like it is in the diagram. Sometimes my guys say they can't quite understand how the diagrams put together because, or like certain things like the parallel sections, the series sections. So sometimes you can adjust it a little bit to make it a little bit easier. Alright, okay. So then we've got on the battery, they say it's 24 volts. The battery has an EMF of 24 volts, so let's put 24 volts on that cell there. And the first thing we're going to do is give these resistors names so we can handle them. So let's talk about this being number 1, number 2, number 3. It doesn't really matter how you label them up, but if we're working together, then we should make them the same, but just so we're on the same page, but it doesn't really matter how you label these up, it's arbitrary, right? And then we want the battery terminal supply voltage, so the terminal supply voltage will be the EMF minus the internal resistance is equal to the terminal voltage. This is not really the internal resistance, this is the current of the circuit flowing through the internal resistor, and that will cause a voltage drop. I just like this formula because it does a one-time thing. It's a one-trick pony, but it does exactly what we need it to do. So it's quite useful, nice and clear to use. We don't have to worry about like voltage drops. I'm still going to calculate the voltage drop over that resistor anyway. I'm going to do it manually afterwards. So it's yeah, I'm going to be doing it twice basically because it doesn't cost me very much to do a quick calculation. I need to know the voltage drops as you go around the circuit in order to get the voltage supplied to this parallel section over here, in order to get the current anyway. But this little formula comes in handy for these kind of questions. It's like short and straight to the point. We're going to be using the usual resistance in series, resistor 1 plus resistor 2, and also resistance in parallel as 1 over resistor 1 plus 1 over resistor 2, and also we're going to be using Ohm's law, of course, all over the place, VIR, here, there, and everywhere. Alright, so this is what we're going to be using, and the first thing we're going to do as usual is we need to work out the current in the circuit. In order to use this formula, we need the current, the I right there. So the usual approach for this is we're going to combine all these resistors together into one big fat resistor. And the first one we're going to combine are going to be these two up here. Then we're going to combine that series section in parallel with this one. and then we're going to combine that combination with these three, like this, as usual. Like I said, it's a usual setup. We've seen this circuit diagram a few times now in quite a few papers, so it's quite an easy, familiar setup. So let's get resistor 1 and 2 together in that parallel section, as I just said. So we're going to be doing the resistance over the series section, and that would be R1 and R2, and we're just going to add them together, right? So the resistance total for this section will be R1 plus R2, which is 40 plus 80 to give us 120 ohms. Okay, great. I'm going to redraw my diagram. Like I said, maybe you can find a shortcut to this. You don't have to draw so many diagrams, but in the interest of clarity, I can copy and paste them as well. It's not too bad for me. Problem for you guys is that you got to draw it clearly in the test. And if you do a scrappy drawing, you do a quick rough drawing, it starts to get a bit confusing and you can't see clearly what you're doing anymore. So this is a new resistor. We've combined these two, the 40 and the 80, into 120 effectively, and now we can cause resistor number 6. It's a new component. Okay, great. So now we're going to combine these two together in parallel with each other. So this would be the resistance over the parallel section, and that will be the R6 and the R3. Like I said, you don't need to write out all this stuff if it takes too long. I just do it for clarity. So this is 1 over RT is equal to 1 over the R6 plus the 1 over the R3. So that will be 1 over 120 plus 1 over 100. We're going to need a calculator for this, so let's get a calculator. Yeah, the other one I just did in my head, didn't I? But check numbers, 40 plus 80, all good? All good, yeah, 120 for sure. Alright, so 1 divided by 120 plus 1 divided by 100 equals, and then we're going to flip it, 1 divided by answer equals, okay, 54.54, recurring. Awkward numbers, different numbers from when we last did this question. So 54.545454 ohms will be those two resistors combined. So just so you can see what's going on, here is, we have now combined those two resistors together into one big fat resistor, and that big fat resistor is 54.5454 ohms, and we're going to call it resistor number 7. We can just keep adding these numbers on here, right? And now we've got all of this in series, so we're going to combine all of these three resistors in series. So this is resistance over the series section, and that will be the R7, R4 and R5. It doesn't matter the order you do them in, it doesn't matter which way the electricity goes either, it's all the same thing, right? Okay, so we're going to say resistance total for the series section will be the R7 plus the R4 plus the R5, so this will be the 54.5454 plus the 120 plus the 3. So I've still got these numbers in my calculator. We can just add the 123 onto it, and we'll get 177.54. Weird numbers. I haven't seen these numbers before. They don't feel very familiar. It doesn't look like it's going to come out to be anything nice, but this is the total resistance of the circuit. I don't really need to draw another diagram because it will just be the battery or the cell and one single resistor. I would normally do that in training just to show it to you, but you don't need to do it. Let's save ourselves a diagram. So now we've got the circuit information here, which is the VIR. We've got the supply voltage being 24 volts. We've got the total resistance of the circuit as 177.54 apparently, which just feels so strange, that number. And then we'll look at the current using Ohm's law. So that will be I is equal to V over R, so 24 over 177. So let's get 24 and divide it by 177. I don't really expect anything nice. Yeah, 0.1351.7. Alright, so the current here is 0.135176665 amps, apparently, going through that circuit. Alright, so that's the halfway point. Usually we have to do a full breakdown and get the currents at points 3, 2, and 1, or 1, 2, and 3. Oh yeah, my guy says he got about the same number that we just did, so that looks good. Okay, And then the current flowing through this point. So I wanted to get the battery terminal supply voltage. So that's why we got this formula, and that's why we got the internal resistance and the ampage. So we might as well calculate this guy right now. So the EMF of the battery is being supplied at 24 volts. You can see it there, 24. The current going through that internal resistor is the total supply ampage for the whole circuit. So here it is, and the resistor, the value of that resistor is 3. This effectively calculates a voltage drop in accordance with Ohm's law. This is V is equal to IR, and this is calculating a voltage drop across that internal resistor. And then this is the battery. If I can draw it on like a big battery, because that resistance is inside of the battery. So by the time we get outside of the battery, we would have lost some of that 24 volts, and that's exactly what we're going to calculate right now. All right, when I say battery terminal supply voltage, yeah, you see they've drawn the dashed line around it to show that's inside the battery. It doesn't explicitly say that's an internal resistor, but it does with the diagram, I suppose. So, okay, great. So let's calculate that. We can times this together, times by 3. This is the voltage drop of about 0.4 volts. So 24 minus that will get us the answer of 23.59. So this is 23.59447 volts is the battery terminal supply voltage. This will be part A. I should probably write that somewhere. This is the terminal voltage or supply voltage to the rest of the circuit. Okay, and this is the voltage drop. All right, that's it for part A. Now to do part B, we have to do a full breakdown, and this is why these questions are a little bit long to get through, or quite long to get through. I need to do a full breakdown of everything in the circuit, basically. Like I said, we can skip the very last step because we just need the amperages, the currents, not the actual volts, but I'm still going to do almost a full breakdown anyway. My process now is to work our way back into the circuit that we've combined all the components together. So we're going to use these 3 circuit diagrams. I suppose I can get them ready to go. Let's just get them one at a time. So the first thing to look at is the voltage drop across each of these components. I literally just calculated it over this one, and it was like at 0.4 volt drop across it. But I want to get all of them. What I need is the supply voltage to this number 7 here, because that's the composite of all the components put together. And again, I could just calculate this one by itself in isolation, and that would be good enough. But I'm going to do all 3 because the voltages should add up to 24 volts. And it's a bit of redundancy in my calculation. It's a bit of extra calculation to check that I haven't made any mistakes, because there's a lot of data here, a lot of numbers, and I don't want to get this question wrong. I don't want to put so much time and effort into it and then just find I got it wrong. So I'm double checking my work as we go along, basically. And it's a really solid system. Like it seems to, pick up the mistakes if you make them. So it's really nice. I do like it. Okay, so this will be. It's just a little bit long and confusing, but there doesn't seem to be a way around that. It's not the method; it's the circuit that's confusing. The voltage drop across each of the components, across the R5, R4, and R7. Okay, so I'm going to write out my component number 5, component number 4, component number 7, and we're going to do VIR for each of them. Okay, so here's my VIR and VIR. It's almost like a little table. It's just a little bit too much data to try to put into a table. You end up with a massive table with like 7 components in it. It's just huge. So the voltage drop is actually what we're calculating, and we know the ampage flowing through this whole section because everything is in series, and we just calculated the ampage down here as being that 0.13. That's over the whole circuit, right? This one here. So let's pop that in for each of them, because the ampage flowing through all of these sections will all be the same. And then the resistance is written on the object. It's written on the components. We've got 3 ohms, 120 ohms, and then the 54.5454. Just checking I've got the right numbers. Great. Now we're going to use Ohm's law to get the voltage drop. So using VIR, the voltage drop will be the current times by the resistance. So we just multiply these numbers together and we should get the voltage drop over each of them. We literally just did this for component number 5 earlier. Like the formula of the EMF minus the IR giving us the terminal voltage did this for us. But I'm going to do it explicitly again because I need the rest of the information about the rest of the circuit. And the reason why I'm doing it again and not just skipping it is because I want to check it. but also it's because it's like a universal technique. Like this method will work for any circuit, no matter what they're asking you. Sometimes they don't ask for the EMF, so the terminal supply voltage. They ask for just the currents, for example, or whatever. I'm still going to do the whole process. It costs me like an extra step. Just did it, and I think it's worth it. 0.0135176665. So the first one has a 0.4 voltage drop across it. The next one has a 16.221198 volt drop across it, across this component here. And then the last one is going to be what? That number, I haven't made a mistake on it, times by 54.5454. So it's got a 7.37 volt drop across it. So this is a 7.37326 volt drop across it. And these voltages should add up to the 24 volts that we started with. Let's see if they actually do, because all the volts have to be accounted for. So we got 7 volts plus the 16.22 plus the 0.4. I mean, it doesn't have to be exact, so I can use lower definition numbers, but it should account for all the volts, which it does. If I made a single typo on one of those numbers, then we'd see that. Okay? And we can't see it, so it's all good, right? Okay, fantastic. So now we've got the voltage drop across each of these components. I'm really interested in this component number 7, which is being supplied with a 7.37 volt supply, apparently. Let's go get that section. Again, you can use your own diagrams again, just reuse them. So what we have just worked out is that the 7 volts supply is for this whole section here. If I draw, if you hooked up your voltmeter over here, you would see a 7.37 volt supply, 7.37326 volts across that section. All right. So now I want to know how is the ampage being split across this section, because we could use a ratio between the 100 and 120, but it's a little bit sketchy, it's a little bit unreliable. So this is much more reliable, I think. So how is the current split over the parallel section over, let's just say R6 and R3? Okay, so let's get the components out over here. So this is component number 6 and component number 3. And we're going to use VIR and VIR. Okay. And we know supply voltage is given as the 7.3726, because we just calculated that. So here's the supply voltage to both of those components. The resistance is written on the components. This is 120 ohms, and this one is 100 ohms. Okay, great. And now we're going to calculate the ampage going through that section. So using VIR, we got I is equal to V over R. So the voltage divided by the ampage for each one. So this will be 0.737326 amps, just dividing it down. And the other one will be a little bit different. Did I mess it up? Yeah, it should be 2 zeros, huh? That's why you shouldn't do stuff in your head. We've only got a little bit of ampage being supplied to the whole circuit, right? It's only like 0.13. Yeah. So I'll be able to see that if I made a mistake, which I did, but I spotted it already. So let's do 7.37326 divided by the 120 to get the other one. Again, all the amps should add up to be the supply ampage. So this is now 0.06144438 amps going through this section, right? If you combine these two numbers, we should get the total ampage applied to the whole circuit if I haven't made any typos. So plus 0.0737326, they add up to 0.1351. And that is a 0.1351. That's the supply voltage which we calculated down here. So ampage to the whole circuit, right? That's what the whole circuit is putting out. So that makes sense. Basically, like some of the amps will flow through one section, some of the amps will flow through the other section. Great, okay. So I think we've actually answered some of the questions on this now, because they wanted to know the amps here and here, and we just calculated 3 and 2. Now we just got to do number 1, so the amps through that last section. Let's finish this thing off, and then I'll write them all down at the end. So there's still one more stage to go, because you can see we're not down to the original circuit just yet. Oh, actually we've got all the information, haven't we? Because usually, sometimes we have to calculate the potential difference, and I have to do one more stage of working. But I know all the information now because we've got this 0.6 amps flowing through that top section through number 6. That's going to be here. Going through, I can draw it on this diagram so you can see it. This will be 0.6 amps, and that was section number 1. This is labeled on the circuit. This is point 1, not component 1, or something like that. And then through the bottom section, through number 3, we had the 0.7 amps over here, and that would be right there, flowing through this section. 0.7 amps here, and I think point 2 was like here. Let's see if we got it on the diagram. Yeah, 1, 2, and then 3 was just before that other 120 ohm resistor. So there's point 3, which is here, which will be the full ampage of the whole circuit. So we're done on the question, basically. Like normally, or usually with these circuit diagrams, we then have to calculate the voltage drop across these components to see the PD across this resistor, and that would be fine as well. This would be 0.3, and it would be one more stage of working, but we're done. So let's do amps at point 1, 2, and 3, and that was 0.1, 0.6, 0.06 amps. 0.2, 0.7, 0.07, and 0.3 was the 4 amps for the whole circuit. And that's the question. That's the answers for it. Okay, so that's part B. Yep, let's put part B at the top. I don't know. We need to do the whole thing. That's part A, really, anyway. Right? Okay, and that's it. The classic question, really classic setup, just different numbers. Haven't seen those numbers before, just kind of awkward. Like why do we have such ugly numbers? But it's just like that sometimes. Especially the new guy, he tends to change up the numbers a little bit, and any numbers should technically work. So he just, I guess, lets his cat roll across the keyboard and then says, "Those are numbers." Technically, they do, and they're not nice numbers. They don't work out nice and neatly, like some of the old classic questions do. Okay. So let's look at question number 9. Okay, question number 9 and 10. Let's make a bit more space on these. Okay, just definition questions. State the difference. State what is the difference between a primary and secondary cell. Charging, recharging, non-rechargeable. Primary is not rechargeable, secondary is rechargeable. And then describe with the aid of a diagram electrochemical action of a lead acid battery. Okay, so definition questions, I won't go into that. I would do the calculations right here, but brush up on your lead acid batteries. I've seen this come up a couple of times in recent papers, so worth knowing how to draw it all out and explain it. Let's see. Everything else now, I was going to say it's going to be pretty easy. Yeah, this is easy. Magnetism is just standard. Okay, it's a backwards calculation. Not really. It's pretty straightforward. It's just this naval architecture is a doozy, and then this one's easy as well. It's pretty simple as well. So we got 2 straightforward ones and 1 difficult one to go through. So state Lenz's law. Well, I'm not going to do that. We're going to do the calculations. So a conductor with effective length. So for this one we're using FBIL sine theta, FBIL sine theta, and also we're using B is equal to phi over A. It's just great. And it looks like it's a little bit difficult, but it's just working out the area. We did this one the other day, instead of working out the flux, which is the Weber's, right? So let's get the ingredients. We've got F, B, I, and L. The sine theta is at right angles, so it can be basically ignored because sine of 90 is equal to 1. So we don't need to include it. Multiplying by 1 doesn't do anything. The force on the conductor is 40 newtons. The Teslas, which is the flux density, is what we'll be calculating. The I, the current is carrying, is 45 amps, and the effective length is 0.5 meters. We could transpose this to be fancy about it. We could write let's not be fancy about it. I'll just do FBIL sine theta, plug the values in, 40, and this will be x 45 times by 0.5. Same numbers I think we had on the last video. Right, okay. For a couple of years difference, but so we do the right hand side first. 45 times by 0.5, we'll get that as what, 22.5, and I'll do 40 divided by that to get my value, and we get this 1.7777 Teslas. Okay, that feels a little bit different, but about right. 1.77 Tesla, and that will be my B value over here, or I calculate that as x. right? Okay, and then so my B is equal to 1.7777, we can call it an 8 at the end, I suppose, Tesla. The phi, I think, is given in the question, because they do say it's 280 microwebers. This is micro, which is 10 to the negative 6. We've also got milli, which is 10 to the negative 3. And these are the only two we're working with as small objects. You're already familiar with milli, because they're millimeters. So this is 280 times by 10 to the negative 6 microwebers. Okay, now it's just in regular Weebers. And we're going to transpose this guy because we're looking for the A, right? So I'm going to multiply up the A, divide down the B, so I could transpose this into phi like this, and it'll just make my life a little bit easier. We're going to have to do that anyway. So 280 times by 10 to the negative 6 over the 1.77777 will give us the area. We're trying to get to the diameter, so we're going to do some pi r squared afterwards and work it out in meters as well. So 1.777, I'll do 280 times by 10 to the negative 6, and then divide that by the answer, and we should get the area. Well, that's absolutely huge. Oh, because I didn't put a negative 6 in there. That's a mistake, isn't it? So let's try again. 280 times by 10 to the power of negative 6, and we'll divide that by 1.777. Okay, and that's much better. And now we got the answer as being the area of the conductor, the cross-sectional area is 1.575 times by 10 to the negative 4 meters squared. And we want the diameter. So this will be pi r squared because we'll talk about solenoids. So we assume that there's a circle, there's a coil, right? And then this is equal to this many meters squared. And to get the r by itself, we're going to work this out to get the radius. Just divide by the pi, and then we're going to square root it. So we can take this number, divide it by the pi. I just move the pi down, and then we're going to square root it as well, because we want to get just the r, not r squared. So let's take that number on the calculator. Here it is. We'll divide it by pi, equals, and then we'll square root it. Push the answer in there, equals 7.8. So I got my radius to be 7.080523 times by 10 to the negative 3 meters. This is the radius. In meters, we want diameter, so we're going to times it by 2 to get us there. And it should be about a centimeter across, so times this by 2, we get 0.014 meters, which is 1.4 centimeters or 14 millimeters, right? It's 0.014161 meters, which is 1 centimeter or 1.4 centimeters. So about the size of your finger, which is what we know is appropriate for the solenoid inside of a fuel injector or thereabouts, which is the kind of things we're working with. So that's the diameter of the conductor. Nice and straightforward. No problems there. We shall look at the next question. Okay, so let's look at the next one, and the next one's really hard because there's a typo on here, right? We've never seen a question like this. We haven't seen one in recent years. I'm not going to say never, because looking back to the papers from like 1996, I might find one like this. I don't know. I don't think so, because it's got massive typos in it. So huge typos like this is probably because it's a brand new question, actually. So if you read it, it's weird because it looks like you can calculate it. And like I said, naval architecture is normally the thing we bank on being quite easy to do. So we think, naval architecture, that would be nice and straightforward. Simple pressure, hydrostatic force calculations, nothing bad there. Normally they're just like one-liners in order to calculate it. But this one is really confusing, and I said it caused some massive problems it appears to in the SQA. They took a long time to get back to us on our results. Normally they take about 2 to 3 weeks. This time they took about 7, or was it 8 weeks? And if you want to get a remark on your papers, you need to contest the results within 6 weeks of sitting the paper. So they basically waited out the administration period, so nobody could contest the results. So everyone got these like bad grades or weird grades, and they're like, "Hey, what happened here?" And you can't even. My guys trying to write back saying, "Can we get a recount or something?" And they said, "No, I'm sorry, the period has passed." But then you just got the results back, so they didn't know about it, so they couldn't do anything about it. It just seems a bit, strange, right? Okay, So let's read this thing through. So a barge is in dry dock as shown like in this picture. The dry dock is rectangular with a length of 70 meters and a breadth of 30 meters. The dry dock is flooded and the barge, which has a beam of 20 and a length of 62, just floats off the blocks when the water's depth is 4.4 meters. The barge displaces this much seawater. This is false, this information here. Of relative density 1.025. Calculate the mass of the barge. The reason why I say it's false is because to calculate the mass of the barge, if you know how much water it displaces, you can do that in one step, just using a density calculation. And it's not worth 5 marks. It's crazy, right? And also it doesn't sit with the rest of the question. Probably. There's a typo in the question, and they don't admit this. There's no official results. No one's ever said anything about this. So it's completely like my opinion and your opinion and general consensus. Basically, I just ask all my students, we all knock our heads together and we try to work it out, right? This one I had to research a lot and find a parallel question on another paper from another course, and I found it. I had to look around and found it because, you know, these things exist. And basically, the question is written wrong. So it's not that the barge displaces this amount of seawater, it's that the dock is now flooded with this amount of seawater. And like I said, if I look it up on other papers, that's what I'll find. So it's the dock is now flooded with this much seawater. I think I can even show that in the question. I mean, apart from it just being like, you know, 5 marks and it's a lot more work than that, I think I can actually show that. Can I actually show it? Because we know. Okay, I think I can actually show it. I'll try. I'll try and prove it as we go along, rather than just saying I think it's like this because I read it somewhere else, or I read a similar style question somewhere else. Um, and because it's written new, like I mean, where do the guys get these? Yeah, where does the SQA get these questions from? Do they write them completely fresh, or there's nothing new ever in life, is there? You just have to. It's all rehashes of old stuff. So I can always find similar questions to it, and that's why I suggest it's like this. Okay, so let's approach the question. See what we can do. The dry dock is rectangular. It has a length of 70 meters, and a breadth of 30 meters. So here, let's draw out the dry dock. It's a massive dry dock like this, and we'll give it some height as well. And then we'll draw the barge inside of this one in a second, but it has a length of 70 and a breadth of 30. Okay. And then the dry dock is flooded, and the barge, which has a beam, just floats off the blocks when the water's depth is 4.4. I am questioning if it's correct to change this, because if you don't if I don't change the wording on the question, if I just say the barge displaces this much seawater, we can calculate the mass of the barge and just basically using the mass is equal to density times by volume. It's one step of calculation, and then the only thing that's stopping me from doing that is if the barge displaces that much seawater and it's this size, does it actually float? Because if it has to be deeper, if it has to be the height of the barge, it might be higher than the water's depth and might not actually float, according to these calculations. I don't think the barge is actually that heavy. So actually, I think that would actually be the case. That's what I'm saying. I can prove it. I can prove that this is an error. Okay, I keep jumping around. Let's just stick to what we're doing. The dry dock is flooded, and the barge, which has a beam of 20 and a length of 62. So I'm going to draw the barge inside the dry dock. We've also flooded the barge. Just floats off the blocks when the water's depth is 4.4. They give us this diagram, which is kind of useless. You know, it has like a thickness to the side of the wall, and so I don't need it. And if we don't notice, you can't see the blocks. This is the like argument or the question from my guys was like, you can't see the blocks. So what are you meant to do? Like, if you knew the blocks, maybe it'd be easier. You know the height of the blocks. Okay, so let's just get the barge, and we're going to draw it in there. So how are we going to draw? Here's a water level, and the water level is at 4.4 meters. Okay, and then we're also going to have, let's draw the water level like this. We're also going to have the barge sitting in there. So I want to get the barge to be like obvious there's a barge. So let's make it like a really clear shape so we can see it. Let's make it something like this. Might regret that. So here's my barge sitting there in the water. Okay, so it'll be like Something like that. There he is. Floating in the water, right? I got it fully submerged, but this is the submerged section of the barge. Let's say that. Okay, and the barge is, we've got some information about the barge. So I can pull the barge out by on its side, on the side, and so we can see it clearer as well. And that'd be nice to do. So let's do that. Let's just draw a picture of the barge on the side. Here he is. A bit sketchy, my drawing. But I'll have to do. Here's the barge. And the barge, we do know it's, what? It has a beam of 20 and a length of 62. 62 and 20. Okay, and I don't know how much is submerged. Okay, because we don't know how high it is. I was able to calculate the mass of it straight away. Okay, so the logic I'm using is that when the dock is filled with water, that volume of the water plus the volume of the submerged barge will give me the total volume of the water. Okay, so I'm going to say the volume of the water, or the volume of the barge, as in the submerged section of it, plus the volume of the water should give me the total volume of the dry dock. I mean the part that's filled with water. Okay, so this is going to make a bit more sense as we look at it, because we do know the total volume of the dry dock, because they did say that the total volume of the dry dock, well, they gave me the size of it, right? They said it's 4.4 meters deep on the water. I mean, think about when the barge is not in there, the water won't be so high, and as you push the barge down, the water is going to rise up the side, right? So that's what we're looking at. The total volume of the dry dock will be the length times by width times by height. So it'll be the 4.4 times by the 30 times by the 70. And this is a big number. And this is kind of how I'm justifying it as well. So let's have a look. 4.4 times by 30 times by 70. We get that as 9,240. It's a really big number. This is 9,240. Okay, the water being added in, I am saying, is this 6,234. So that would be 6,234. Okay, now we can work out the volume of the barge that's been submerged. That's going to be what I call it X. So let's get rid of that X. I'm going to put volume of the barge here. Okay, let's calculate this one first of all. But do you see we can get the volume of the barge from here quite clearly? It must be displacing this much water. It mustn't be displacing that much water. And like I said, I can probably prove that that number's just wrong. So I'm going to minus off the 6,234, and now we get the volume that the barge is displacing is only 3,006. So the barge, so X is equal to 3,006 meters cubed. This is the volume that the barge is displacing. This is volume of the barge that it displaces. So from this we can calculate the mass of the barge quite easily. But we had to put it together like that. So let's do that. Let's get the mass of the barge. So mass of barge, we'll be using the DMV, where mass is just going to be the density times by the volume. We've got the density because we're flooding it with seawater of 1.025 like usual. So 1.025 times by the volume, which is 3,006. Okay. 3,006 times by 1.025. So it's 3,000 tons and 81. 3081.15 tons. This is the mass of the barge. Okay. Right, like I said, if we just use what it says in the question, the barge displaces this much seawater, then we'll get 6,000 tons. And I think if I try to float that in that much water with this breadth and length, it will be higher than the water is. I reckon it'll be like 5 meters. I can prove that, but it's a bit of a side calculation, and I don't really want to do it in the middle of the video. But let's finish this thing off, right? I would just do it straightforward. So that is literally the mass of the barge. I'll finish it off and then I'll go back and do that. So that's part A. That's the mass of the barge. Okay. Now the pressure on the bottom hull plating, assume the barge to be a rectangular box barge. Well, I already assumed that. The pressure on the bottom hull. So I need to see how deep the barge is sitting in the water. Because again, we don't know that. We know the height of the water. We don't know the height of the blocks. Otherwise, we just subtract them and we'd be done. Because it says it just floats off the blocks. So that would be like the equilibrium point. Yeah, we're going to calculate the height of that barge now, which is quite standard and straightforward. It's just with all the typos in the question, you know. It doesn't make it easy. So let's do that. Let's get this out of the way, and we'll calculate the draft of the barge first of all. The pressure. So to get the pressure, I need to know the draft. I need to know how deep it's sitting in the water. So first of all, we'll calculate for part B. We'll calculate the draft. Let's make some space on it. So find draft. Okay. I know the volume it's displacing. The volume of the barge was down here at 3006. So the volume is 3006, and it's also the length times by width times by the height. The length and the length and the width are fixed, and the height is not. So this will be 3006. This is a normal calculation. Times by 62 times by 20 times by x. We multiply this together, divide it down. We'll get the draft of the barge. So 20 times by 62 equals, and then 3006 divided by that will get me the draft. It's only 2.42 meters deep in the water. Okay, 2.42419 meters is equal to the draft. So it does sit nicely inside of the dry dock. We got this big space underneath. You could maybe 2 meters, maybe walk underneath it, maybe get some work done. Seems all right. Find the draft. Okay, so from there we go to the pressure, because it's asking for the pressure on the hull plating. So pressure is equal to rho GH. This is our H. So the density of the water is 1025. We'll do it in pascals, times by 9.81 and times by the 2.42419 meters. Nice and easy. All right, there it is. The height times by 9.81 times it by 1025, and we get this in pascals. For every 10 meters we go down, we expect 1 bar of pressure. We only went 2 meters down, and that's why we only get 24,375 pascals. So it looks about right. Okay, that's going to be the pressure. And that's the end of part B. So that's the entire calculation, but with the typo it makes it impossible to do, basically. And you can stumble around the question and lose time, and then I think the question is completely discounted anyway at the end of the day, because it's a mess, right? Now so that's the end of this. You can skip to the next part if you want to. I'm going to try and justify, just for fun, that this is actually correct, because I'm going to try to justify that the barge would have to be like more submerged, and also if the barge did displace that much seawater, it would have to be really tall, and it would be so tall it wouldn't sit. It would sit out of the water. It wouldn't. It would sit on the bottom of the dry dock. It wouldn't be on the blocks. I think it might be because it's quite deep, right? We've actually got quite a large gap. We've got this. Yeah, but that's like the volume is 3006, and this is more than double, so it's going to need more than. The draft will be more than 2.4, so it'll be 5. So yeah, it will sit on, it won't float. It won't float. So let me justify that. Okay, so this is a little bit extra. So let's just see if we can do that. Let's just say the barge does displace this much. First of all, I can get the mass of the barge from this straight away. This is the problem with the question, is you can just say the mass is equal to density times by the volume, and the mass of the barge would be, because it's displacing salt water at this density, you just multiply these guys together and you're done, which is definitely not worth 5 marks. 1.025 times by 6234 gives me, so we've got a heavier barge now. It's now 6389.85 tons. Okay, that's fine. Let's work out the draft of the barge if that was the case. So, if I just did that for part A, I was like, yes, I'm done, on to the next bit. We're going to have to work out the draft for part B, right? So the draft is the volume, which is equal to, we do it from the volume, the length times by the width times by the height. It's the height that we're calculating. The length and width of the barge are fixed, just the same as we did here. Right, it's going to be 20 and 62, exactly the same. We're calculating the height, but we've got this new volume. I'm using a different volume, not the tonnage, but okay. So the volume is the 6234, and the length of the barge was 62, and the width, the beam, was 20, and the height we're going to calculate. And I reckon the height will be higher than the water, will be higher than 4.4. So it will need to have deeper water in order to float, deeper than we have available. So we do 20 times by 62, and then we do 6234 divided by the answer. We get the answer as 5.03. Yeah, I was right. luckily. So 5.034 is equal to the height required in order to float that object, and we only have 4.4 meters deep of water. So you sit there scratching your head in the exam and going, "What can I do about the situation?" And you can't because there's a typo on the question. So really difficult to tell, like, because in the most recent papers in 2025, in the 2024 papers, it looks like they got this under control now, but there's a lot of typos in the 2023, 2024 papers. Actually, you got to be really careful about them. I should highlight which ones have the typos on them because you can't do the question. It's a waste of time, right? In the paper, so if you see a typo, but you can't even see that typo. It's so screwy. All right, that was number 11. Oh yeah, on this number 11, I mean, it's only ever come up one time like this style of question. By all means, we can study it. They might have fixed the typo and now they're ready to release it again, but I have never seen it ever come up. We get this quite often in the papers. You get these one-time events, these one-time questions that you just never ever see ever again. And the question is what to do about it. Do we study it? That's basically why I'm making these videos, so I would have to spend class time going over them because I don't think it's worthwhile because it takes a long time to go through them to explain the mistakes, fix the errors, and then actually study the proper question, and it might not even come up, and it's quite unlikely, I think, that it will come up. So what we study in the classes are the most likely ones, of course, right? Okay, on to the last one, which is the standard normal one, hopefully with no typos in it. We've got to be a little bit careful. So a vessel has a displacement of this much seawater. It's a rectangular fuel tank 10 meters long, that wide, that deep. The tank is now full. The tank is full of oil with the density, and it's 1.2 meters above the keel at the tank bottom. A kg of the vessel is this much when the tank is full. Calculate new kg after all the oil has been used. So this is unbunkering, using up the fuel. So we're unloading the vessel. So let's draw a quick cross-sectional diagram about what's going on so we can get our head straight on it. And then we'll get the table. And we'll just fill in the table. And it should be okay. It's just a little bit backwards to what we used to, right? It's not really an issue because we're actually expecting these ones. We do look at these in training, so it's just fine. There's three different situations. You can be loading or unloading, and the load can be above or below the center of gravity of the ship. And then the worst one is you got to find the mass itself, which is a really hard question. So I just train my guys up to identify it as being a difficult problem, and then we just don't do it. We choose not to do it. You don't really have time to do everything on the paper, every single question, so you can choose your battles. And the good thing is on the GES 2 is that normally you guys are trained up to do everything on the paper, not like GES 1 where we have to take some we got to make some decisions about what to study, basically, because there's a lot to do in GES 1. Okay, a vessel has a displacement of this much seawater, rectangular fuel tank that long, this wide. Oh, it has a single rectangular fuel tank. I drew it as two. So I was going to say it's quite wide, isn't it? Like 8 meters wide, 4 meters deep, and the bottom is 1.2 meters above the keel. And then the kg of the vessel is here. And that's kg. It's 6.2 meters when the tank is full, and then as the tank is emptied, I expect the kg to go up. So this will be the new kg up here. Yeah, it's going to raise the center of gravity. It's going to be a little bit higher, and it's only about 5 centimeters high. Not the calculations, most of them are like that, not always. I know there's 12 or 10. Okay, we've also got to have the center of gravity of the tank, right? And because it's completely filled until completely emptied, so the kg of the vessel when it's full of fuel oil. Calculate after all the oil has been used. So it's completely filled or completely emptied. So the center of gravity is smack bang in the middle, and that will be exactly 2 meters or halfway of the height because it's a uniform load. So it'll be right there in the middle, like that, right? If it was a half full tank, it would be a bit more complicated, and we got to think about it a bit more. But it's not. It's just like this. And it hasn't been so far. I don't never say never, but okay, right. So we've got all our data basically ready to go. Let's get that table out because the table is giving me a bit of guidance about how to feel about what to do next. Basically, it's a bit of a crutch, a bit of a help to think what do I do now. So we've got name of the objects, and we're going to have the ship. We're going to have the load, and ship plus load always. Okay, we're going to have the mass and everything be done in tons because we're talking about ship size objects. We normally have a force column here. We don't need the force column really, so I'll just put it in small and then cross it out because we can just keep everything in mass in this one. And then we're going to do force times by distance. So this will be the kgs. The distance will be done in meters. Okay, and this will give us a moment. When you do a force times by a distance, you get a moment. And this will be done in ton meters. And then we're going to have the direction that things are moving in. So we're going to have clockwise, anti-clockwise. So this will be direction, and this will be anti-clockwise and clockwise. This will be the turning moments or the righting moments, right? The thing's trying to roll over effectively. Okay, great. And we're always going to have the ship plus load versus the ship and the load. So we can put like clockwise, clockwise, anti-clockwise. It doesn't really matter which way around this goes as long as the top two are opposite the bottom two. And that's it. Now we're going to start filling in the bits of data. Do we know the mass of the ship? No, we don't, but we know its displacement. So let's do a calculation for mass of the ship. Now this is the mass of the ship when it's loaded. I gotta be a little bit careful and go a little bit slower because this time we're unloading the vessel, right? So the mass of the ship, this would be mass of ship plus load, and we're gonna use dmv. We know the volume, so the mass is gonna be the 1.025 on the density times by the volume of the 19,000. Right, and that's when the ship has is full of oil as well. So we're going to take 1.025 times by 19,000, and then we get 1947.5. This is equal to 1947.5 tons. That will be the mass of the ship plus load. So we put it in here, 1947.5. Okay, great. Now, do we know the mass of that fuel tank when it's full of oil? No, but we know its dimensions, so we're going to calculate it. So let's do the mass of the load, or the mass of the tank, mass of the oil. I'm going to call it load. And this will be the same thing. It'll be the mass will be the density. The density of the oil is 900 kilograms, so that'll be 0.9 tons per cubic meter. And it'll be length times width times height. So the length times width times height is 1084. 8, and 4. That will be the volume of the tank multiplied by its density, and it probably goes about 288 tons because it always seems to. 10 times by 8 times by 4 times by 0.9. It always gives us the same numbers, which is nice to know because it means we're on the right track. It's when the numbers get changed and it gets a bit spooky. So 288 tons is that load, 288. And this one time we're going to work it backwards, right? Because we need to work out the mass of the ship when it's unloaded. So what's 1947.5 minus a 288? We're going to unload it to get 1918.7. So 1918 and 7. Okay, now the distance is going to be those kgs. This is the leverage it's getting. So the old kg, when loaded, that was 6.2. The kg of the load is going to be the 1.2 distance between the bottom of the tank and the keel, and then the extra 2 meters to get to the center of the tank. So that's 3.2 meters here, right? 3.2. So this will be 3.2 meters. The new kg is what we're calculating when all the oil has been used. So that'll be this one here. Okay, so that's basically the hard work done. Now we're just going to go and fill in the rest of the bits of the table. Just give it a bit more space on the side. Alright, we go to fill in these parts here, which means just multiplying things across. So the 1918.7 times by x will be this, and the rest of them I can't do in my head, so let's get a calculator. So 288 times by 3.2 to get the moments, 921.6. And then the other one at the bottom there is going to be the 1947.5 times by 6.2. Is a bit bigger, so 120745. We are technically taking moments about the keel, so let's say it, and then to solve this we're going to say, as always, the sum of the clockwise is equal to the sum of the anti-clockwise moments, as always. Okay, fantastic. And we're going to pick up our parts. So these two here are the clockwise, the ship and the load. So let's put them next to each other and add them together. And then that will be equal to the the ship and load working the other direction, anti-clockwise. We're going to minus off the 921 and then divide by that 1918.7. So I got this big number in my calculator, minus off the 921.6 equals, divide that by 1918.7 equals 6.245. Nice number. So x is equal to 6.245 meters. This is the new kg after all the oil has been used. I do expect that the new kg is going to be higher, it's going to go up, right? Because we've got rid of some of the ballast. So the old kg was 6.2 meters and when it was loaded, and now it's gone 4.5 centimeters upwards as we've unbunkered the fuel, used up the fuel. Calculate the new kg after all the oil has been used. Well, that seems right. This is the new kg. It's gone in the direction we expect it to. And that's the whole setup. And that's the end of that paper. Some tricky questions on there, some tricky typos. I think it's one of the hardest papers for the GES 2 in the most recent years.